So, good morning, everyone. I am Payal Vadwa from IIIT Vadodara. Today, I am going to talk about on-the-fly training, finite temperature properties with first principles accuracy. So, I believe I am the only person who is going to talk about machine learned force fields. So, I will be taking things from the scratch, and I will be using some real life analogies to make things simpler, which I generally do for myself, but I hope it may help you too. So, before I move ahead, I must mention that many of you might be using VASP for DFT calculations. So we should thank Georg. You might be citing him. So he is the father of VASP, also my postdoc supervisor. And whatever the work I'm going to show you today, that I worked during my postdoc tenure at the University of Vienna. In yesterday's talk, Professor GP Das mentioned that out of 100 top cited papers, 12 papers are from DFT. And I'm glad to mention that out of those top 100, Georg stands on eighth. So, and this is the new logo of WASP. So let me move to my work. As my title is Finite Temperature Properties with First Principles Accuracy. So the question arises, what is this actually finite temperature problem which we are facing with the traditional methods? So as we know, density functional theory predicts properties at the ground state, right? But experiments do occur at finite temperatures. And to capture these effects, we use ab initio molecular dynamics. So in ab initio molecular dynamics, DFT calculation is performed at every time step. So it is computationally very expensive. Also, it treats nuclei classically, propagates through Newtonian equations of motion, and it follows Maxwell-Boltzmann statistics. So it misses low temperature effects like zero point energy and tunneling. So it is not that accurate at low temperatures. So the question arises, can we determine finite temperature properties with first principles accuracy and with the reduced computational cost? So today I'm going to discuss one of the methods to address this issue, which is laid upon the foundation of the discovery of these two gentlemen, John J. Hopfield and Geoffrey Hinton, who were awarded the Nobel Prize in 2024 for the discovery of artificial neural networks, which was inspired from the functioning of neurons in a human brain. Now, before jumping to machines, let me start with how we train a human brain. So, a teacher trains his student by giving them lectures or assignments for a couple of weeks and months. Then, whenever a teacher, then to take their test, whether the student is trained properly or not, he takes their test, which lasts for a couple of hours, right? Now, if the test goes well, it means the student is trained well. But if the test doesn't go well, it means either the learning or the training is improper, right? In the similar manner, machine algorithms are being trained in which we give them input in the terms of reference configurations and parameter optimization for a couple of days, weeks, or months. It may vary upon the problem. And once we get enough training data, then we take the test. Then again, if the test goes well, it means the algorithm is trained well. But if the test doesn't go well, the reason is again the same, that either the learning or the training is improper. Now, in material science, one of the applications of machine learning is the generation of force fields. Now, as its name suggests, machine learning is used to determine the energies and forces of atomic structures with nearly first principles accuracy. Now, before discussing its mechanism, let me take a very general example of daily life. So suppose if I ask you to train an algorithm to determine the age of a child based upon his height, what will be the initial steps you take? First, you will collect the data, right? Then, I think there is one line missing. Yeah, first you will collect the data. Ideally, I don't know why it missed, but there would be one line. Then our next step would be fitting that data, right? Once you fit the data, we don't care where our original data was. And then suppose a random child comes to you and tells you his height, then you can immediately tell what his age is, right? This is the journal principle. Now, the similar principle we follows for solids as well. What we do, what is the first step? Collection of at least 1,000 first principle structures. Then we need to make sure that those structures must be readable by the machine, right? So we need to convert those structures into machine readable language. That is, we need to choose a local environment which is also known as descriptors. Like bond length, it is for 2 body descriptors. Like for bond angle, we need to use 3 body descriptors, and so on. Then we need to fit that data using neural networks or regression methods. Like you can see here, first is the collection of database, then we need representation of atomic environments, and then we need to do the fitting. And then suppose a random you get a if you somebody gives you a random structure, then you can immediately tell what its energy is. So now what is the problem? Problem is the application of machine learned force fields are still limited to simple materials. Why? Now suppose if I ask you, this is the structure with you, this is simple bulk structure, or this is simple surface, or this is simple the adsorption of something on the surface. If I ask you to generate 1,000 first principle structures out of this, it would be very complex, right? It's not that easy. Simply from these structures, creating 1,000 structures is not that simple, right? So data selection and parameter optimization are complex, and it need a lot of hit and trials, right? Now, to add, what is the simplest thing you can think of? Just heat the system, atoms will vibrate. So once the change in position would be large, when the change in atom position would be large, take that new structure and add it into the database. So this is how on the fly training works. What we do here is we perform the MD simulation. We heat the system, forces change. You can see error in the forces. Once this error in forces crosses a certain threshold, then first principle simulation is performed. It means we are relaxing that structure, and that relaxed structure is being added to the database. But if it is less than this, then simple MD simulation is being performed. So what here MD simulation is doing? MD simulation is just helping us to explore a large phase space, and first principle is relaxing that structure, and that structure is being added to the database. So you can see here that here we can explore wide phase space, and it is very systematic data selection. Another thing you can see here that in journal MD performs DFT at every step, but here we need almost more than 99% of the first principle calculations are skipped, right? So it is nearly 100 times faster than traditional ab initio molecular dynamic simulations. Furthermore, we can predict finite temperature stable configurations out of it, and this technique is implemented in WASP. So now the thing is, suppose you train the force fields. Now you want to determine the stable configuration at finite temperature, or you want to study the structural phase transition, which one of the guy was asking yesterday. So what we need to do? We need to use global optimization algorithms for this. So one of the global optimization algorithm is simulated annealing. You might know about annealing, right? You have read it in your school days that if we need to convert this gold bar into gold ornaments, we need to do first quick heating and slow cooling. Simulated annealing is nothing but the simulation version of it. What we need to do? We need to cool the system slowly, then the energy will decrease, right? And we can from here we can get the it can trap into the global minima. But with this method, it can happen that the system may trap in some of the local minima. So to overcome this issue, we use parallel tampering method. There is another more efficient method which is known as parallel tampering. So how it works? Suppose we are working in a group, and the same problem is being given to many people. They all are working on the same problem, but in their own ways. After some time, they discuss with each other, exchange their solution, and then start working on again independently. And then they discuss again, and then again exchange their solution, and then again started working independently until they find the robust solution. So of course, this method would be more efficient instead of a single person trying the problem, right? So similarly, in this parallel tampering, one simulation is being run, multiple replicas of this simulation is being run at different temperatures, and after some time, they exchange their solution and then run again. So with this method, high temperature simulations are being accessible to the low temperature and vice versa. So it leads to a more robust solution. So this is mainly the optimization method which I have used in my work. So what problems we can study out of it? So suppose you have a complicated STM image like this. This is the STM image of cuprous oxide 111 surface. So let's see what DFT can suggest out of it. This is the normal bulk structure of Cu2O, and this is its 111 surface. We can see here, of course, when we will cut its surface, it will be losing its uh, next bulk counterpart, right? So of course, the atoms on the surface um, will have dangling bonds, right? So they will not be that stable. And if you look at from the top, you will find that it is simply forming a hexagonal structure with one this dangling atom in the middle. But so this is the actual this is the thing which we generally, if we cut into if we just make a 111 surface of it, and it is the structure we can expect from Cu2O 111. But what you can see here in experiments, what they found is there is something copper cluster in the middle of this. And previous studies have said that this is by adding Cu4O cluster into copper deficient system. So of course, this system is not easy to predict using DFT, right? You need to make a lot of hit and trials out of it to predict this structure, right? So, can we find an easy alternate? Let's see if on the fly training can help. So what the methodology we followed, we trained the force fields on a stoichiometric structure with the minimal functionals. Then we constructed various stoichiometries and performed global optimization algorithm, parallel tampering driven by machine learned force field. What I'm trying to say here is, let me go to this slide. Like original stoichiometric configuration means perfect Cu2O combination, like 132 coppers and 66 oxygen. I trained the machine learned force fields on it, and then I constructed various another stoichiometries, means other perfect Cu2O combinations or copper deficient or oxygen deficient. Then we performed global optimization on these structures with this force fields. Is it sound promising to you that I created potential energy surface of this, and I am performing global optimization on some other stoichiometries? It may not in journal. So of course, from this you can get the lowest energy structures. To overcome this issue, what we did is we added some structures from the copper deficient and copper rich states and generated second generation machine learned force fields. And from this second generation machine learned force fields, we performed another global optimization with this, and we found that the lowest energy structures from this as well as this, there was no change in the both of the two. And from each of these structures, we calculated their surface energy and then plotted the phase diagram. So whichever the surface is having the low energy, that would be the most stable one. So let me discuss it in detail how we did. So this is these are the various stoichiometrics which I consider for square root 3 square 3 as well as 2 by 2 supercell. And these are the resulting configuration. Let me discuss this in detail. So mainly what I did is I trained the force fields by heating the system up to 1400 Kelvin, from 50 Kelvin to 1400 Kelvin. So we overall got 1645 configurations. So these are the error metrics. You can see here energy and forces obtained from the machine learned force fields as well as from the first principles follow a straight line. Also, the errors from the training set as well as stress test set are also in good agreement with each other, indicating the robustness of the machine learned force fields. So, force fields is ready. Let's perform the global optimization. Then we perform the global optimization. So this was the original stoichiometric configuration. When we relaxed this structure using machine learned force field, so you can see here that this is a simple hexagonal structure with this center atom is little bit distorting from the little bit away from the center, means it is breaking the center of inversion symmetry. And when we perform the global optimization on the same stoichiometry, we found this copper cluster. Of course, you can never predict this kind of structure using DFT if you relax it. And then we performed global optimization, that is parallel tampering on other stoichiometries as well, and this kind of copper clusters we got. When we performed on this copper deficient configuration, we found that unstable coppers is getting eliminated, and this was also in agreement with the previous observations. Then we performed for oxygen deficient, we found that oxygen was getting eliminated from the subsurface layers. If you would be performing DFT In DFT, we will perform for vacancy from the first layer, from the second layer, from the third layer, whichever would be having the lowest energy, that would be the most stable one, right? But with the machine learned force fields, it automatically leads to the structure where vacancy is in the subsurface layer. And this is also in agreement with the previous reports. Then comes this nanopyramidal configurations. So when we performed parallel tempering simulation on this stoichiometry, we found this copper cluster arrangement similar to the one which was being in STM image. You can see here that 3 coppers in the middle. So here this is like this, and this topographic height is also in agreement with the experimental value. So of course you can imagine how would you know that experiments are having if you cut bulk, you will simply have that normal arrangement like 1 copper atom in the middle, but you would not know that we need to add something, whether it is copper rich or copper deficient, right? So with the help of machine learned force field, we were able to get it very quickly and in a more efficient way. So but as I already told you that we trained machine learned force fields on a minimal stoichiometry. So then we generated another generation machine learned force fields by added some of the structures from the copper deficient and copper rich states. So from here you can see here that it is also again like energy determined from machine learned force field. First principle calculations are again following the straight lines, and this is the principal component analysis, where this x-axis determines the composition and y-axis determines the distortions, or we can say diversities of the structures in the machine learned force fields. And this clearly indicates that our machine learned force fields has diverse structures, contains a lot of distortions or so. So, and when we perform PT simulations from second generation as well, we found that ground state configurations remain unchanged for all the stoichiometries under second generation machine learned force fields driven PT simulations. So what it indicates that our original force fields, which we just took from the minimal configuration, is robust. So then we plotted the phase diagram, like you have ground state energies of various configurations, right? But which one is actually the most stable one? To determine that, we plotted the phase diagram using first generation force fields, second generation, as well as first principles. We can, of course, the lowest one would be the most stable one. You can see here this copper deficient and this pyramidal of copper deficient. This blue one and maroon one are having intersection at minus 1.67, and here it is at minus 1.55. Of course, first generation is good in determining their structures, but if you want to determine the energy, then second generation would be better because it has more structures of copper deficient as well as copper rich. So their intersection point indicates that they are in our model is robust. So it is also in good agreement with our experimental collaborators provided value at like 1.5 Kelvin. So what it indicates that on the fly training provides a robust and efficient method to determine complex surface reconstructions commonly encountered in experiments. Now, if you want to look at this paper, you can, if you are interested in this paper, you can have a look at this paper. Let me move to the another problem. Suppose if you want to adsorb something on the top of a surface, what you will do? You will try possible positions, right? Here, here, or here, whichever would be having the lowest energy, that would be the most stable one, right? But with the machine learned force field, you don't have to do that. Just train the machine learned force fields, perform global optimization, you will automatically get the most stable structure. So this is, we found that for one monolayer, it automatically follows the linear chain, and for then we can also study the coverage dependence. We added 2 monolayers, and here we found a zigzag pattern, and this was in good agreement with the previous theoretical and experimental reports. We can also determine the IR frequencies, just generate the machine learned force fields. So for this IR, then there is one flag in VASP, you can easily find in VASP wiki. From that you can determine MLFF driven IR frequencies, which is very quick actually. So these values are also in a good agreement with the experimental values, again indicating the robustness of the machine learned force fields. Another problem you can discuss is, you can study is like negative thermal expansion. Suppose if you heat a solid, what do you expect? Ideally, it should expand, right? Its volume should increase. But copper Cu2O, cuprous oxide, is a material which has negative thermal expansion. That is, its volume first increases and then decreases. It means it is robust against thermal stress under heating in electronic devices. So you can see here, this is from the previous reports. Like we can see here that here volume first decreases and then increases. So it means it is following a negative thermal expansion. And what previous studies have suggested, theoretical studies have calculated these values using quasi-harmonic approximation and PB0. PB0, you can imagine, PB0 is Hartree-Fock of 25% exchange, right? And in general, these thermal expansion calculations are being done on a supercell. So you can imagine the computational cost of the supercell with 25% exchange, right? So it would be like, it will take months, right? But also the experimental values have shown this value as minus 10 ppm per Kelvin, parts per million. So again, here we train the force fields. Once force field is ready, we perform the NPT simulations driven by force fields. As I already mentioned in the first slide that um, already mentioned in the first slide that MD fails at low temperatures, so NPT couldn't capture this negative thermal expansion. But when we perform this QHA with PB, we found this negative thermal expansion, and we can see here that this value is minus 11, which is in good agreement with the experimental reports. So overall, if what else you can study? You can study to calculate the melting points, thermal transport and phase transitions. One of the guy was asking, so you can have a look at this paper. You just need to train the force fields, perform the MD simulation driven by force fields. From there you can get it. There are many cases in which PB is not that good, right? So you need to go for higher functionals, HSE or RPA. So in this case, you can learn the delta learning. Yeah, that is, you can train the force field on the minimal functionals, and then out of those structures, just train higher level correlation on some minimal structures, and then you can learn the delta. So for this delta learning, you can consult this paper from my group, and you can also study the coverage dependence. For this, you can have a look at this. You can also find a lot of capabilities of machine learning from Georg's Google Scholar page. So overall, I would like to say that on-the-fly training provides us a powerful and efficient method, alternative to full ab initio simulations with a very reduced computational code, and that is, it is nearly about around 100 times faster than the traditional ab initio simulations. With this, I would like to thank University of Vienna, Georg, our experimental collaborators, my colleagues from the VAST team, and TACO and IIIT Vadodara for the financial support. Last but not least, organizers for giving me the opportunity to present my work, and audience for your kind attention.
Thank you, Dr. Bhagavan. Sorry, I showed up a little late because I was chairing another session for the review talk, and I was completely oblivious to the fact that I had to come here. So we'll take questions now.
So as I understood, on-the-fly software or technique, it is different from DFT calculation.
Yeah, this is.
It's like molecular dynamics.
It is a combination of MD as well as DFT. So below threshold it is MD, above threshold it is DFT, but yeah, it is just it. Let me go to that slide, which I showed in the beginning. Yeah, you can see here. Below this threshold, it is MD. Above this threshold, it is first principle. So it is a combination of both.
Yeah, good. Any other question, comment? Yeah.
Thanks for the talk. I had one question regarding this, like whatever when we are applying neural networks, we would try to reduce the loss function compared to the standard that we have. And the standard that we are getting is via first principle calculation.
Okay.
So
yeah.
How does that incorporate all the complexity of a material that you are trying to get? Like
See,
it is like it is carried out on a much smaller scale. So how can it have the full complexity of the system that you are doing?
First, I would like to mention that this on-the-fly training is based upon the regression. if you make your own model like neural networks, like if you use graph neural networks or so, then of course either you can use active learning, or you can means accelerated data driven simulations, right? So if you make this machine learning interatomic potential, so it is the same way, only the fitting is either regression or neural networks. So of course neural networks would be more efficient, like mace is using neural networks, but as I'm from the developing team, so I would like to explore the capabilities of this methods, and we found that it works almost really great in many cases which we tried. Yeah.
What the question? Yeah, yeah. Please. Are you speaking to the microphone?
From pre-existing at least 1,000, more the better. And like we want to heat you, like we can heat the system to get that. Why, like, is it so? Why can't we like train the model on the already existing structures from the same family? Like yeah, that is like this is active learning. The one which you are saying, that is data driven. Yeah. So here mainly it is the machine learning interatomic potential. These are like, you can use both the terms, machine learned force fields or machine learned interatomic potential. So you can see here this is nothing but interatomic potentials, right? So the one which is you are saying, that is accelerated data driven approach. Yeah, this is active learning. Okay, thank you.
Okay, so if there are no further questions, comments, let's thank Dr. Wallo again, and let's move on.